Hello, Phil Truby here. Following my Cybertruck Etherloop investigation, thought I'd give you folks a look at the technology behind Starlink. Conceptually, it's pretty straightforward, but when you peek under the covers, it gets progressively more fascinating, intricate, and impressive. Let's start with an overview. Here we are with your laptop, cell phone, or computer. It's connected either via Wi-Fi or wired Ethernet to a Starlink antenna, which I'll call a user terminal since it includes both the Starlink router and antenna. The Starlink antenna takes your request packets, like looking at Netflix, and sends them up to a nearby Starlink satellite. The satellite then resends the data packets down to a nearby gateway station. The gateway station is then connected via a high-speed fiber connection to a large data center run by Google or others, where it is then handed off to the internet. At this high level, what I've shown you is a generic satellite communication system that we've had since the 1960s. And here's where we start to dig into what makes Starlink different. Traditional satellite communications use geostationary satellites that orbit around the Earth in an orbit such that the satellite stays over the same location relative to the ground as the Earth rotates once per day. So the satellite is orbiting, i.e. moving, around the Earth, but the Earth is rotating underneath it at exactly the same speed, leaving the satellite stationary relative to the ground. The problem with these geostationary orbits is that they are over 22,000 miles above the Earth, which is almost the same as the entire circumference of the Earth. And this matters because it takes about a half a second for a radio signal to go and to come back from the satellite at this distance. This delay makes it impossible to use for gaming, Zoom conference calling, even just voice conversations are annoying with this satellite lag. So what Starlink did was to put the satellites around 300 miles above the Earth. This gives you a lot of advantages over geostationary satellites. Round trip time is 70 times shorter, 7 milliseconds instead of about half a second. But this introduces a new problem. Due to the way orbital mechanics works, the closer you orbit a planet, the faster you move relative to a fixed point on the ground. And so Starlink satellites are zooming around at 17,000 miles per hour. Put another way, any given user terminal typically can only communicate with a single Starlink satellite for a few minutes before it disappears. Here's a simulation showing this in action. This oval is the Starlink user terminal on the ground, and these dots are the satellites zipping around in space about 300 miles above the ground. A user terminal can only talk to one satellite at a time, but this shows all the ones it could communicate with. This simulation also shows which gateway the Starlink satellites could be communicating with. So in this example, this satellite communicating to this user terminal would be bouncing the data packets to this ground-based gateway, which is then eventually connected to the internet via fiber optic cable. Here's what the entire Starlink constellation currently looks like over the Earth. As of mid-2025, there's over 7,000 satellites delivering service to over 6 million customers in over 110 countries. Now, some people look at this map and worry about space pollution. Isn't space going to end up being littered with all these satellites, especially as they reach the end of their service life? In a word, no. First of all, graphics like this aren't even close to scale. If the satellites were depicted using the same scale as the Earth, you wouldn't be able to see them at all, since each satellite is about the size of a car. I mean, here's a zoom into a random spot in the United States, and you can do this 1,000 times to find that there aren't many cars around, even though there are over 1 billion cars in the world versus only 5,200 Starlink satellites. The point being that space is huge and can support a huge number of satellites. The other advantage Starlink has is that at their 300-mile altitude, there is just enough atmosphere to drag down the satellites if they become incapacitated. In the jargon, the satellites will self-demise and burn up in the atmosphere, and it'll look like a meteor burning up completely before hitting the ground. That's what happens when something traveling at 17,000 miles an hour hits our progressively thicker atmosphere as its orbit decays. Let's now dig into the technology Starlink uses for this part, from user terminal to Starlink satellite. We now know that the user terminal is constantly hopping from satellite to satellite in the sky. It normally flips between satellites every 15 seconds, although if there's an obstruction that pops up like a tree swaying in the wind, it can transition to a new satellite in 1/10 of a second. You've all seen old-school dish antennas used for things like satellite TV. They are built in a parabolic shape to concentrate the relatively weak radio signals. Unfortunately, Starlink can't use such antennas since it has to move the antenna way too quickly to hop between different satellites. So a major Starlink innovation is to use a phased array antenna. These have been around for many years, but typically only used for specialized applications due to their high cost. Instead of a single radiating or receiving element at a focal point amplified by a simple metallic dish, a phased array uses hundreds of elements. When sending, an onboard computer chip tells each element to be slightly out of phase with each other, such that the signal power is steered in almost any direction. Since the steering is all electronic, the antenna power can change direction within microseconds, while the physical antenna itself doesn't move. These video clips are courtesy of an excellent video about phased array antennas and how they work, which is linked in the description below. So unlike a geostationary satellite dish, which is just a cheap hunk of metal, the Starlink antenna is very complicated. So much so that when Starlink first launched and it was selling their kits for $1,000, it was estimated that each user terminal cost about $2,500 to make. This is no longer the case as Starlink's manufacturing volumes have ramped. So, we have a phased array antenna for customer user terminals. The satellites also use phased array antennas to quickly steer their signals. Each Starlink satellite has 3 antennas to broadcast data to 3 areas at the same time using focused spot beams. These areas aren't exactly small. Each beam area is a smeared circle with a 15-mile diameter. And each satellite can steer their beams to dozens of different areas. A centrally coordinated algorithm ensures that each 15-mile circle gets an adequate share of data sent down to it from the closest satellite at any one time. Every user terminal in that 15-mile diameter circle sees all the data intended for everyone in that circle. But of course, the Starlink router will only forward packets intended for the correct user. For data going back up to the satellite from the user terminals, Starlink uses a strict time slice protocol. It allocates small periods of time where any one particular customer can transmit up to the satellite. Okay, let's talk about the gateway now. You might have noticed this mushroom farm-looking thing that I call the gateway. Here's a big picture of it. What are these things and why 9 of them? All right, first of all, the white domes are just a weather cover called a radome. It's to keep snow and rain off the internals. And here's what it looks like inside. Surprise! We finally have a traditional parabolic dish as part of the Starlink system. Parabolic dishes are used here since gateways constantly communicate with up to 8 Starlink satellites at the same time. This many phased array antennas so close to each other would produce too much signal interference. So higher performance and narrower beam parabolic dishes are used instead. There's 9 of these so that any one parabolic antenna only needs to track and communicate with one satellite, which is something that tracking motors can do. A parabolic antenna will slowly track across the sky, pointing at the passing satellite that it is tracking. A gateway site can communicate with up to 8 satellites, while the remaining parabolic antenna does a large repositioning to start communicating with the next satellite to come into view. By the way, Starlink uses different radio frequencies to transmit up and down from the gateway and up and down from the user terminals, so that some of these transmissions can happen at the same time. There's about 100 gateways across the US, with about that many more around the world. Gateway sites can be located both in urban centers and in remote locations. When located in rural areas, they are often co-located with fiber optic repeater stations, since gateways need very high bandwidth back to an internet data center. Cross-country fiber optic signals need to be amplified every 100 kilometers or so, and these repeater stations are dotted around the country, making them great places to place a Starlink gateway. Next up, the point of presence, or POP. Starlink rents space at these highly internet-connected data centers to run a bunch of computation tasks for data flowing into and out of the Starlink network. The computers in these massive buildings make sure that you're an authorized user, data is encrypted, and headers are compressed. And valid internet addresses are assigned to your data packets via network address translation as they exit Starlink's computers at the POP. Starlink provides service literally everywhere, including the North and South Poles and in the middle of the oceans, locations that are much too far from a gateway for a one-satellite hop architecture to work. To get around this, Starlink's satellites have optical lasers and receivers such that the data packets can be routed from Starlink satellite to Starlink satellite for as many hops as it takes to reach a satellite that can communicate with a gateway and thus onto the internet. This is very much like running fiber optics in space, except that no fiber optic cable is needed since the vacuum of space doesn't interfere with laser communications. There's no air, rain, snow, or fog in space. Most people think of Starlink as a home internet service, but Starlink is now offered for many different uses. Airlines like Hawaiian, JSX, United, Qatar Airways, Air France, and Air New Zealand are or have announced plans to offer Starlink in flight for their customers. Almost all major cruise lines use Starlink, including Carnival, Royal Caribbean, and Norwegian. Businesses of all types use Starlink, including oil rigs, construction sites, even industrial farming. So, is there anywhere Starlink can't be used? Yes, and this is something that many people get wrong. While Starlink is amazing, It is only cost competitive against other forms of internet access in sparsely populated or rural areas. Starlink is too expensive and slow relative to fiber and other wired broadband offerings in cities. The fundamental reason for this has to do with the wildly different information carrying capacity between Starlink and optical fiber. Starlink uses radio frequencies between 10 and 52 gigahertz, and it can't go much higher than that because the atmosphere starts to absorb higher frequencies the higher you go. Optical fiber, on the other hand, uses light running at around 200 terahertz. In other words, optical fiber uses a frequency about 10,000 times higher than the radio waves that Starlink uses. There are other factors at play, and optical fiber can't actually carry 10,000 times more information yet, but you get the idea. The point is, it can carry a heck of a lot more. There's also the major problem of beam interference. Each Starlink spot beam is a circle about 15 miles across. Only one satellite can be transmitting into that spot at any one time. I won't bore you with the calculations, but Starlink could probably support a maximum of about 8,000 customers in that 15-mile diameter circle. Silicon Valley's San Jose urban city limits is about the same size as that 15-mile circle, and about 1 million people live in San Jose. A far cry from the 8,000 or so that Starlink can support. The point being that wired internet, be it fiber or other broadband, is the only solution for dense urban cities. Starlink is used in cities, but mostly by businesses that need hot standby emergency backups in case of local fiber cuts, or other situations where wired internet is expensive. Starlink is constantly improving. Each SpaceX rocket carries about 30 new Starlink satellites at a time, and they launch about once per week. This translates into better service, as this bandwidth and latency chart shows. Average bandwidth has tripled in the last 3 years, while latency has halved. This has resulted in an ever-increasing subscriber count, as all these new satellites are continually improving customer experience. Unlike geostationary satellites, which are big, expensive, and have 20-plus year lifespans, Starlink satellites are only expected to last 5 years, which means that SpaceX is continually refreshing the installed satellite fleet with newer and better satellites that deliver new services. 2 years after satellite version 1 satellites, SpaceX added inter-satellite laser links to offer service over the oceans and to other remote areas. Next came a 4 times bandwidth per satellite bump, and the newest version of satellites provides direct-to-cell service. Direct-to-cell is SpaceX's latest service, which currently provides texting from any regular phone, literally anywhere on Earth. It works via partnership with local cellular service providers. Let me conclude this high-level technical tour of Starlink with how it fits in with SpaceX's mission. As you may have heard, SpaceX has one and only one mission, and that's to make humans a multiplanetary species by colonizing, not just going to, but colonizing Mars. And that's what the Starship program is all about. It's a fully reusable giant lift rocket. But way back in 2012, when Elon Musk was talking about an early version of Starship, back then he called it the BFR, or Big Effing Rocket, he had the problem of how to fund its development. Starship and its associated Mars mission is at least as ambitious as the Apollo program that put astronauts on the moon. An endeavor, I'll remind you, that cost at its peak over 2% of the entire GDP of the United States. Elon realized two things. One, SpaceX would rapidly hit a revenue ceiling launching satellites into space. It's a finite market which wasn't going to grow past a certain point. Second, a lot of the satellites he was launching for others were communication satellites, and providing communication services was a much bigger business in terms of revenue. So Starlink was conceived for the following strategic reasons. As a business, it could be 10 times the size of SpaceX's launch business, providing much needed profits to spend on Starship. It would require a huge increase in the number of launches needed, so this would further lower the cost of the SpaceX launch business itself. It would synergistically use SpaceX's low-cost launch to hopefully avoid bankruptcy that befell previous satellite constellations like Iridium, Teledesic, and Globalstar. Of course, both the Starship and Starlink programs needed lots of upfront investment money before they would eventually make money back for SpaceX. In 2015, Elon convinced Google to invest $1 billion on the strength of the Starlink business plan. 5 years after Starlink first went operational, it is now profitable for SpaceX, an amazing achievement for a communications infrastructure company. And SpaceX isn't done yet. Starlink is still growing. I fully expect it to double in size from here and double again in the next 5 years. Thanks a lot for watching. If you have any questions or comments, please ask.